Let's go ahead and do a hypothesis test on one sample. So let's read here. California spends an average of $9,660 per student with a standard deviation of 1,324. This is K through 12 education spending. A random sample of 86 California school districts serving a majority of students of color had an average of $10,249 in state and local revenues per student. So they had, looks like a little bit higher on average just from the 86, a sample of 86. Is this different from the state average and what can be concluded at the 5% level of significance? All right, so let's go ahead and set up our hypotheses. And our null hypothesis, again, here we have an average. So I'm going to do something a little different. I'm going to change this from different to more because just to do a different example in our class here. So so we're going to say, is the average $9,660 per student for these school districts that have a majority of students of color, or is it more? Is it more or is it not? So the question might be, if you're watching this right now, is yes, it is more. It's 10,249. It is more than 9,660. But it's possible that we just took a sample that was low, right? I mean, it's of course it's possible. I mean, you sometimes we average, sometimes you get a sample that has a low average, and sometimes you get a sample that has a high average. So the question is how probable was it to get a sample of 86 with 10,249 if it wasn't more? So let's go ahead and do the math for that. All right, so this is a we're going to use a z-test here because sigma is known, the population standard deviation is known here. We have the standard deviation of 1,234. So I'm going to go ahead and draw my normal curve, and this time the normal curve represents all samples of size 86 of the school districts. The sample means, if I take samples of size 86 school districts in California, these are the sample means of the average per student in the school district. Okay, so it's, again, we are going, if we have size 86, we'll have some that are down here, we'll have some that are up here, but let's go ahead and continue our drawing. So we assume that this is normal, or the central limit theorem says that if we have n greater than or equal to 30, then we have a normal distribution. The mean of the means is this population mean, 9,660. We're assuming the null to be true, and our standard deviation or standard error is approximately 142.77. So I'm going to do one standard deviation above and below the mean and compare where my sample is. My sample obviously lies to the right of this. It's definitely greater than z equals 1. It's definitely more than one standard deviation away. Let's go ahead and see how many standard deviations away from the mean is this, away from the null is this. So I'm going to calculate my z value, and my z value is 4.13. That's large. That's not to scale there. That's definitely way out in the tail. That, I can tell you without even looking at my critical values, we're going to reject the null. We're going to say that's too unusual. It's definitely greater than, it's like if maybe 10 out of 100, if we have a 5% significance level, if 10 out of 100 came up like this, it'd be, oh, not so improbable. But this is improbable. We have a 4.13 test statistic. So for our critical value, we look at our alpha. Alpha is 0.05 here. So 0.05 to the right means 0.95 to the left. This is a right-tailed test. So for it's a right-tailed test, I'll do my inverse norm of 0.95. I get positive 1.645. That's definitely, again, means I reject the null. This test statistic falls in my critical value. All right, so if I do a z-test, enter all the information on my TI-84 calculator. My p-value was 1.36 times, or e negative 36. That's times 10 to the negative 36. That's 35 zeros and then 136. Let's, for all intents and purposes, call that 0. If I were to use a free calculator online to calculate the p-value for this, I would click on the normal calculator in Canvas. The mean is 9,660. The standard error, or standard deviation, was 142.77 approximately. I want to know above, let's see, and the value was 10,249 was my sample. And the area, or the probability, was approximately 0. It doesn't even register on here. It's so many zeros. It was the 35 zeros and then 134. So our calculator is just rounding it to 0. That's definitely less than 5%. We're going to reject the null. So our conclusion was we reject the null. It's not it's not 9,660. In fact, there is sufficient evidence to show that the mean payment per student in districts with majority of students of color is greater than 9,660. On average, they get more than that. Okay, so if we rejected the null. If we made an error, if this was a mistake, it was a type 1 error. If it was a mistake, we might have rejected a true null. So in this case, we would say that there was actually a difference. Actually, sorry, that there was a greater than. That it's not difference. It's that the mean for students of color, mean for the district of the students of color, that it was greater than 9,660 when it actually wasn't. Okay, so a type 2 error is to fail to reject a false null. So if I fail to reject a false null, I didn't make that error here because I didn't fail to reject the null, but I'd fail to show, again, it's not a difference, but I'd fail to show that it was greater than 9,660 when actually it was greater. So the probability of a type 2 error is beta. The probability of a type 1 error is alpha. And in this case, alpha is equal to 0.05. That's the probability of rejecting a true null, saying that there was greater than 9,660 when it actually wasn't.